Now that we know about dynamically allocating memory, we can create linked lists for times when we want to store a bunch of things of the same type, but we don't know how many we're going to have. The idea behind a linked list is that we create one node for each thing we want to store, like one position of an array, but instead of storing them contiguously, we allocate them as we need them, and we make each one have a pointer to the next one so that we can find them all. We always have to keep a pointer to the first node, which we call the head of the list, and sometimes we need a pointer to the last node, which we call the tail of the list. Since the last node does not have a node to point at, we make its next pointer null. List is a standard data structure, and it supports these kinds of operations: the ability to create an empty list, which is one that has no nodes in it yet, the ability to add another node either at the head or at the tail of the list, and the ability to print out the list. Those are what we're going to talk about in this video. In the next, we'll talk about finding things in the list, deleting a node from the list, and strategies for keeping a list in sorted order. To build this in C, the first thing we need is a struct for a node. For example, suppose we want to keep track of a list of players who are identified by their player IDs and have experience points. We need a struct that holds the player's information and a pointer to the next node. Notice that the type of that pointer is the type of the struct we're writing. I've also wrapped our struct declaration in a typedef statement so that I can give our struct the alias player node, just to make our code more readable. Now that we have nodes, a list just needs to keep track of the nodes. We do that by keeping a pointer to head node and a pointer to the tail node. Again, sometimes we don't need to keep track of the tail, but I will in the videos just to show you how it's done. So, both of these pointers point to our player node struct. Let's connect back to that original picture. Each of these is a player node, and those are the pointers to the next nodes. And our list struct contains the head and tail pointers. Now we're ready to build some stuff. This is how the standard data structure operations that we're talking about in this video get implemented in C. Create empty list returns a pointer to a list T struct. The two functions that add new data to the list get passed a pointer to the list that should be updated and the data that should go in the new node. And print list just gets passed a pointer to the list struct for the list that it should print. Let's look at each of these more carefully. Creating a new list is pretty easy. When someone wants a new list, they just call create empty list and store the pointer that it returns into their list variable. In create empty list, we use calloc to allocate space for one list T struct. And then I like to null the two pointers. Calloc already zeroed them, so maybe that's overkill. Then we return a pointer to the struct that we allocated. When we add more data to the list, we're going to need to create new nodes. So let's make a function for that. It should take the data that goes into the node, in this case the player's ID and their experience points, and return a pointer to a node that has been initialized with those values. This code is very similar to create empty list. We calloc the space that we need. Now in this case, zeroing is silly because we're going to put the data we want everywhere, but I like being consistent about using either calloc or malloc. In general, calloc is safer, and for these tiny structs, the zeroing is really cheap. Then we fill in the player's ID and experience points and set the next pointer to null. The node is created, and we return a pointer to it. The first way that we can add data to the list is with add at head. We could build a list using code like this. It first creates an empty list, and then it adds two nodes each at the head of the list. As it adds each one, it should create a new node and then link it in at the head of the list. This is the empty list that we get from create empty list. When this code adds the first node, since the list is empty, we just have to make both the head and tail pointers point at the new node. When it adds the second node, we have to make a new node and make it point where the head is pointing, and then make the head point at the new node. You can see now our head node points at the first node in the list, which points at the second node in the list, and the tail node also points at the last node in the list. Let's do that again, looking at the actual code for add at head. Remember, this is called after we have created the empty list. We pass in a pointer to our list, that structure that has the head and tail pointers, and the values related to the player we're adding. The first thing this code does is create a new node and store a pointer to it into player. Then it looks at the head pointer. In this case, our head pointer is null, so it will execute the else block and make both the head and tail point at the new node. The second time we call it, it again creates the new node. Then it looks at the head pointer. Since the head pointer isn't null, it copies the head pointer into the player's next pointer, so the player is pointing at the existing node, and then makes the list head point at player. The order in which we play with the pointers really matters. Let's watch what happens if we reverse the order of these two statements. We used those when we were adding the second node, so before we got there, our system looked like this. Now suppose we moved the head pointer to point at player before we copied it into player's next pointer. That feels kind of okay, but we've lost the rest of the list. We no longer have a pointer to that second node, so we can't reconnect to the rest of the list. When I play with this kind of pointers, I always have to draw the picture to make sure I'm not making this kind of mistake. The next function we want to look at is add at tail. Instead of adding the new node to the front of the list, this should add it to the end of the list. This time, let's look at the code first. Here's the code for add at head so that we can compare the code for add at tail. Their parameters are exactly the same. They both create a new node the same way. And when the list is empty, they both do the same thing. The only thing that is different is these two lines of code that encode how we attach a new node when the list isn't empty. To see what those two lines do, let's keep them visible and watch how they work. Here's a list that isn't empty, and say we're adding this new node. The first line says, start at the list struct and follow the tail pointer. That gets us to this node. Then make its next pointer point at player. Let's do that again. List points to tail's next pointer should point at the player. That hooks the new node into the list. Then the second statement makes the list's tail pointer point at that new node. Since it's the tail, it should point at the last thing in the list. Now, just like with add at head, if you do those two statements out of order, the list becomes disconnected. Draw that on a piece of paper to see why. Now that we can put stuff into our lists, we need to see how we'd find that stuff. To show you how to walk through a list, let's write the function that will print the contents of all of our nodes on our list. It will take one parameter that is a pointer to the list node. We'll just need to make a local variable hold the head pointer. Then we can print the stuff from the first node. Store the next pointer into our local variable, and we can print out the second. Store its next pointer into our local variable, and we can print the third, and so on, until our local variable gets to the null. So, that's a sentinel controlled loop. The condition to keep going is while our variable isn't null, and we set our variable to its next pointer to move through the list. This is what that looks like with the details fleshed out. That's my intro to linked lists in C. Here are the functions I'll talk about in the next video.